Hi, this is Siling Gao from Natural Language Processing Lab at EPFL University. Let me introduce our new work of VinaBench, a benchmark for faithful and consistent visual narratives. Visual narrative generation aims to transform a textual narrative into a sequence of images that illustrate the content of the text, which is a task often involved in human literary and artistic creation. For instance, in the film and television industries, screenwriters usually write their stories into scripts, and then art designers visualize the scripts into storyboards to assist the filming of movies and TV series. However, for vision language models to become good visual narrative generators, two fundamental challenges need to be addressed. The first challenge is narrative alignment, where textual narratives are often abstract and visually underspecified, which causes manifestation gap between the input text and the output vision. For example, the action of cooking in the text is visually underspecified, which needs to be depicted by specific background of kitchen and probably an apron in the character outfit. In the second example, the bad news mentioned in the text is an abstract object, which needs to be implicitly interpreted as a sad expression on the character face. To fill such manifestation gap, models must conduct common sense inferences to ensure relevant and coherent visual narrative generation. The second challenge is about visual consistency, where narrative elements such as characters and locations may be connected across different scenes or images in a visual narrative. For example, the two images shown here are closely connected in the narrative, where the basic settings of their scenes remain the same, which is Samantha staying in the same kitchen. Models must plan such discourse features in their generations and be consistent in how these features elements are manifested. To address the above challenges, we propose a new benchmark, VinaBench, which augments existing visual textual narrative pairs with knowledge constraints. We first incorporate common sense constraints, which use common sense links to bridge text and vision to ensure the visual narrative generation is faithful to the input textual narrative. Specifically, we use dense image captions to describe visual details in each narrative scene, and then construct the links to align visual entities in captions with their associated entities in textual narrative, such as sad expression linked to bad news in the third scene. We also incorporate discourse constraints, which capture the narrative elements that may be connected across different scenes, to ensure that these elements are consistently manifested. Specifically, we annotate global discourse constraint features that include character attributes and image appearance style, which are expected to remain static throughout the narrative. We also annotate scene-specific discourse features, which trace the dynamics of basic narrative elements, including the presented characters, time of day, and location of each scene. Our incorporated common sense and discourse constraints offer scaffolds for learning faithful and consistent visual narrative generation, and meanwhile facilitate the evaluation of this task. So for evaluation, prior full reference metrics such as clip embedding similarity directly match model generations to gold reference images, which may skew the evaluation to irrelevant details in the specific gold references. For example, the model generation shown here is in far different image style compared to the gold reference, which may achieve very low similarity score. However, it is still a feasible generation aligned with the input textual narrative. Besides, prior metrics possess no consistency measure of visual narratives, which may overlook inconsistent flows in the model generation, such as inconsistent outfit of the same character in the first and second generated images. To address these limitations, we propose a set of reference-free VQA-based metrics based on our annotated knowledge constraints to more closely access visual textual narrative alignment and visual narrative consistency. Specific queries of our VQA-based evaluation are listed here, including 5 alignment aspects and 3 consistency aspects. For experiments, we test 3 baseline vision language models that are optimized for visual narrative generation, including StoryGen, ARLDM, and MM-interleaved. We evaluate these model generations with and without the augmentation of our VinaBench knowledge constraints. If without VinaBench constraints, shown as the green setting, vision language models are fine-tuned to generate the visual narrative directly based on the input textual narrative. If with the augmentation of VinaBench constraints, as shown in the orange setting, a large language model is first fine-tuned to predict the constraints based on the textual narrative, and then vision language models are fine-tuned to generate the visual narratives based on both the textual narrative and the predicted constraints. Our results demonstrate that learning with VinaBench knowledge constraints significantly improves visual narrative consistency and alignment to input textual narrative. However, visual narratives generated by vision language models obviously fall behind the gold references colored in the yellow setting, indicating still a large room of improvements. We also conduct a human evaluation that rates each visual narrative on a Likert scale from 1 to 5 with respect to 5 aspects, as shown in the left chart. Our human evaluation supports the results of our automatic evaluation. Furthermore, we study the correlation of different automatic metrics to the human evaluation, including the average of our alignment and consistency metrics, shown in the third and fourth rows of the red heat map. Compared with the measure of clip embedding similarity to the gold reference image and to the input text, denoted as clip I and clip T metrics, shown in the first and second rows of the heat map. The correlation coefficients heat map demonstrate that our proposed alignment and consistency metrics have better correlation with human evaluation. This slide shows an example of visual narratives generated by our strongest baseline model, interleaved, with and without the augmentation of our VinaBench knowledge constraints. We find that with the learning of VinaBench constraints, as shown in the green circles, the model generation shows richer details and is better aligned to the story and lab settings described in the text. However, as shown in the red circle, the generation still suffers obvious inconsistency flaws, such as the inconsistent outfit of the character Nicholas, indicating the room for improvement. In summary, we propose a new visual narrative benchmark, VinaBench, which provides a reliable ground for generative vision models to learn faithful and consistent visual narratives with discourse and common sense constraints. In view of the shortcomings of visual narrative evaluation, VinaBench also includes new evaluation metrics to more closely assess the consistency of visual narrative generations and their alignment with the input textual narrative. Our experimental results demonstrate that learning with VinaBench knowledge constraints effectively improves various vision language models at generating more self-consistent and faithful visual narratives. However, our results also indicate that model-generated visual narratives still have considerable room for improvement to reach the level of human visual storytelling, which raises the call for future study on more robust visual narrative generators. Feel free to find our paper on arXiv and in CVPR 2025 proceedings to check out more details. Our data and code are also publicly available now, which are accessible from our project page. Also, feel free to check our lab website for more updates of other recent projects and publications. Thanks for your attention.